Hello there, this is Dizzy, and it's time to play some Minecraft. So today, in our sort of continuing NuclearCraft saga, I want to build an automated control circuit for our reactor. And we're going to use something called automated redstone to do this. And I'm pretty excited about getting into this because from what I've seen of it, it might do just what we want in terms of allowing us to really finally control the reactor. So that's the project for today, and we're gonna see what happens from there. Now, since we last sort of were talking, I have managed to manufacture LEU, so low enriched uranium 233, which is more powerful, as best I can tell, than the LEU 235. And you can see I'm now getting 2,000 RF a tick with 0 net heat. So that means that it runs at 2000 RF and generates no extra heat, but we are basically just staying on top of the heat. So we're at the point now where, given that this is running on a server and it's chunk loaded and all that fun stuff, I want to make sure that there is a fail safe to shut the thing down in case, for whatever reason, our heat or our cooling stops working. And we're going to want this anyway as we try to burn hotter and hotter fuels. So since we met last time, I did that. You can see I started playing around with automated redstone a little bit. This is a sensor that's actually tied to this energy cell. So if I flip this on, you can see it starting to build up RF, and that's 100. So that's 135,000 RF. So it's 1,000 kilo RFs as it's running. And so that's pretty cool. We're going to use that sensor to actually determine when to run the reactor as well. I've also gotten into bonsai trees, so I've got a little tree farm going over here, which is pretty cool. If you haven't played with bonsai trees, it's really great. It's, this has been running for a while on a chunk loaded server, but it's a little probably overpowered. But I like the aesthetic. It works, and I don't know. I just kind of like it. It's one of those mods where, yeah, it's a little overpowered, but that's all right. I've also set up this sort of drawer system to enable us to sort of better track clumps and chunks and all that stuff. As you can see, and I've burned a couple of different fuels at this point. So I've managed to get plutonium. We've had neptunium last time, and I got a little bit of americium as well. Americum? Yeah, americum. I don't know. Anyway, and you can also see that I have enabled the radiation system in NuclearCraft, which is something we're going to have to think about as we burn more stuff. But other than that, not too much that I've done. So the next step then is to go ahead and start getting an automated redstone. So what we want to do is the fission reactor controller, the fission controller, actually outputs a redstone signal. So if you put a comparator next to it, it will output a signal, if a stronger and stronger signal based off of how hot it's running. So once it gets up to sort of, if the temperature gets up to sort of halfway, critical, the output signal will be about 7.5, 8. And when it hits critical, it'll be 15, which is obviously very bad. So what we want to do is measure that signal coming out of the controller and use that to turn the controller on and off. And that will actually allow us to build unstable reactors and do other fun stuff. But the other thing that we want to do is we really want to only run the reactor when we absolutely need it. And so I also built this thing, another part of automated redstone, called a energy valve. So you can see right now that the power is 142 or whatever in the upper left-hand corner there. That's showing us how much RF is moving into our network from the reactor. So it's generating the network is pulling 140 RF a tick or so. Now we do still have this other, this other system, which isn't frankly running very well, which is probably just because I haven't done the phytogrow stuff, but I've been more interested in NuclearCraft this round. So we can now actually measure how much the draw is. So what we want to do is run the reactor, fill up this buffer, and then let it drain, and then repeat, because we're going to generate, we can't use 2,000 RF a tick most of the time. And so that would let us sort of make our fuels last longer because we're only using them when we absolutely have to. That's what we want to do, and we're going to use automated redstone to do it. So we're going to build a comparator that's going to feed into an automated redstone thingamajig, and then we're going to design some circuits together, which should be fun considering I don't have a EE background, and you can watch me again fumble around. So for starters, for automated redstone, let's take a look at that mod real quick. There's a bunch of stuff in here, but we're going to need a circuit designer so we can design circuits. We're going to need a circuit assembler so we can actually take the plans or schematics that the designer generates and plug them into the assembler, and the assembler will then make what we need and pop it into a circuit casing. This will make a lot more sense as we get into it. So I'm going to need to set up auto crafting for all this stuff. And then this is a schematic, and then we'll get into sort of designing the circuit together. So let me go sort of make the designer and the assembler and set up auto crafting for some of the other components, and then I'll be right back. So I have done all the crafting and automated crafting that we need, and as part of that, I've gone ahead and built a circuit designer and a circuit assembler. And then in the assembler, I've filled it up with the components we're going to need. So what happens with the assembler is that once you make your schematic, you get your casing, you put it in here, it processes through, and you get the circuit embedded into this casing using these components from your schematic. So you'll see how this works. I've also gone ahead over to the reactor, and I pulled out 2 of the redstone coolers. So it's now heat positive. And I wanted to do that because I wanted to show sort of the output from the comparator, if I can put that on there correctly. There we go. So the fission controller will output to the comparator a signal. And so if we put some redstone there, and we put a lever back on here, and we go ahead and turn this on, we should be able to see this redstone light up as the heat builds, right? Remember, it's so now we've got some heat, power is 1. And you can see there at 1, we're at this much heat. And then as the heat builds, it'll go up to 15. So I just made it positive so that we could actually test some of these circuit pieces. So let's go ahead let's just talk real quickly about what we want the circuit to do. We want it to, if the lever's on, and the heat is below a certain point, and the energy buffer is not full, reactor should run. If any one of these conditions is false, though, we want the reactor not to run. So if the lever's off, the reactor should never run. If the temperature is greater than some number, the reactor should never run. And if the energy buffer is full, it should never run. So that's what we're going for. Let's go design a circuit to do that. So I've got some schematics, so let me go ahead and put one in there. It's blank right now. So let's start with just the lever or the switch and the temperature. So we're going to define 2 inputs here. And I recommend that you name these. So I'm going to call one temperature, and I'm going to call one switch. Okay. And then what we want to do is we basically want to compare the temperature. So we want to say if the temperature is less than a certain number, then emit a signal. Because if it's greater than a certain number, we want it to be basically off. In the same way that the switch is going to emit a signal when it's on. So what we're ultimately going to do is use an AND gate, right? So I'm going to put an AND gate on here. I'm going to make it just 2 inputs, so they're just 2 red ones. And so the second one is going to go into the switch. So if the switch is on and the temperature satisfies some condition is also on, then output a signal which will activate the reactor, okay? Because AND gates require all inputs to be true. So now for the temperature, we want to do a comparison. So there is actually a less than in here. And the less than says that it is active if the upper input value is smaller than the lower input value. So let's put a constant in here, okay? Because this constant tells us how much heat do we want to allow. So let's say we're going to let the heat get to 3. So any point of 3 or higher is going to cause the reactor to shut down. So what we're going to do is see how this is blue and this one's red, and use the mouse wheel to move it. That's how you toggle the inputs. So then we're going to go ahead and right click here to say temperature goes into the upper, and toggle it again, and constant goes in the lower. So it says if the temperature is less than 3, output a signal. And coming down here, we want to output that signal into the AND gate. So the AND gate will fire if the lever is on and our temperature is less than 3, which is perfect. That's exactly what we want. So let's add an output now. Nope. And then we connect it to the AND gate. So when the AND gate is on, in other words, the temperature is good and the switch is on, output a redstone signal. That's the circuit that we want. So let's save this now. And then we're going to switch over to the assembler GUI. And we're going to take our casing that we made. And I did an accelerated casing because it lets you, it sort of reacts faster. And given that we're controlling a nuclear reactor, we would like quick response times. And you just drop it in the upper. And you can see it did some assembly. And now it is assembled. And actually, you know what I should have done here? Let's call this energy thermostat. Okay, and let's rewrite this. Let's put it back in here, and then we're going to rerun this because now it'll say energy thermostat, so we know what circuit's inside this. So now we have that redstone circuit that we just designed here encased in this circuit casing. So it's like a bunch of redstone in one little block. So what we're going to do is we're going to put that casing right here. Let's take the switch off here. So the temperature is going to feed into the side. I want to put the lever on the front. And then what we're going to do is we're going to run a wire underneath into the fission controller to activate it. But first, let's get this thing configured. So you just click on the energy thermostat circuit, and we're going to say the input temperature is going to come from the side. The input switch is going to come from the front. And then we're going to output a signal, so the activation signal, out the bottom. And then when we're ready, we're going to turn this on by clicking this. But we're not going to do that just yet. Let's go ahead and install our wiring first. So let me just pull up some of these blocks here. Let's see. All right, so the other part of automated redstone is it comes with redstone wires. So we want to have a receiver wire right here because it's going to receive the signal from the casing. And then we want to have an emitter wire over here because it's going to feed a signal up into the fission controller. And then we use the solid redstone wires to connect these. And so now what's going to happen is that when the lever's on and temperature's low, it's going to emit redstone out the bottom and back up into the fission controller. And that will activate the fission controller when those two conditions are met. So let's just go ahead and we're going to come back to the buffer in just a moment because that part of the circuit is probably going to be fairly complex because we actually have to implement some interesting stuff. So what we should see happen, right, and we want to test circuits, especially on nuclear reactors, when we flip the lever on, this should activate because the temperature is low. But then a few minutes later, it's going to turn back off even though the lever's on because the temperature will have climbed, and then the temperature will come back down and then it'll reactivate again. So let's see if that happens. Oh, it didn't. Why? I know why. We never activated the circuit. So let's turn the circuit on. We're going to crank down the tick interval as short as we can to, I guess that's 1/4 of a second. And that's important, especially when you run sort of heat positive reactors. You have to have fast response times because sometimes they generate a lot of RF very quickly, but also generate a lot of heat. So let's try this again. We've activated the circuit now. And you can note the reactor turned right on. Awesome. It's building up heat. And if all goes well, in just a moment, it should shut off. As that heat builds. And there we go. Now it's cooled. The comparator flips and it turns back on again. Pretty cool, huh? So now we have a safety net, if you will. You could do this with normal redstone too, I should add, but it's not going to be as compact, and it gets a lot more complicated when you want not just 2 inputs, but you also want 3, which is sort of the next phase. You can see it's just running a little bit at a time right now, which is fine. There's no, from what I can tell, there's no penalty for sort of switching it on or off beyond what it might do to the server. So now we want to tie all of this together with this energy buffer. Now, it's worth noting that there is a buffer here too, right? Like there's a buffer in the fission reactor. I think it's 1.8 million RF. But here's the problem. So this fission controller outputs a signal when the temperature is high or the internal buffer is full. So conceivably, this circuit would work as long as your energy or it could work, right? But what's going to happen is that if you are heat positive, it will overflow this buffer eventually because it's the heat takes priority. So it's only when it's heat negative does it output a signal around the energy buffer. So we don't want to waste energy either. So the next step is to use the readout of this buffer, feed that into our circuit as well so that we can actually use that to determine when to activate the reactor. Now, you can see over here that I've built with automated redstone a signal, or sorry, not a signal, a LED, and then I've got this sensor reader on top. And the sensor reader is linked to our energy cell. And you can see that right now it's got 4,300, right? And if we look at here, it's about 4,300, right? RF stored in it. I mean, that's 43,000. Anyway, numbers. But so what we want to do is we want to basically take this sensor, slap it on the side of our circuit, and use that. And the trick is that we want to run for as long as possible off of this energy cell. We don't want it to stay full necessarily because we want to run our reactor as little as possible. So let's go back over to our circuit table and figure out how we're going to do this. It gets a lot more complicated. So let me just sort of... how am I going to do this? I think actually I'm going to sort of cram everything in over here because I think we're going to need some room for all of this to work right. So ultimately, we still want the AND gate. We just want to add one more input so that all of our inputs are true. The trick here is that what we don't want to have happen is we don't want this thing flipping on and off all the time. So if we just say, hey, when the energy buffer is greater than X, right, then turn off. That's one way of doing it. But what's going to happen is it's going to try and keep it right there, and it's going to constantly be running. Instead, what we want is we want to say, look, we want to charge the energy cell up to a certain point, and then we want to let it drain to a lower point before we turn things back on. And for this, we're going to need a form of a flip-flop switch, which we're going to implement by hand. It's really basically just an AND gate and an OR gate with a little bit of feedback into it. So let's go ahead and get set up for that. So we're now going to have another input. Wait, where did it go? Oh, sorry, put it in a weird place. All right. So we actually have just one input, I think, right, which is going to be our energy. So let's go ahead and call this E. And that's going to come from that sensor. It's going to feed the energy value into us. And we're going to scale that number sort of using the sensor, and I'll show you how to do that in a minute, to a number between 1 and 18, because is it 18? Yeah, it stores up to 18 million RF. So we want to scale it from 1 to 18 because if we don't, we have to get into 16-bit numbers and things get complicated. So we're going to do that. So the input's going to be a value between 1 and 18, or 0 and 18 as the case may be. And what we want to do is basically if our energy is, let me think through this for a minute. If our energy is above our upper threshold, so we sort of have an upper threshold and a lower threshold. So if the energy is above the upper threshold, the system should turn off. If the energy is below the lower threshold, though, it should turn back on. So let me just sort of write down some scribbles so that I don't have to take you through every piece of reasoning this out. So I'm going to be right back. 1 minute. Okay, I think I've got this figured out. We will see how confusing and how confused I get in the process of this. So remember, we have sort of two thresholds, right? We have an upper threshold, which is 18 million RF, and we have a lower threshold of energy, which is 1 million RF. So this is talking about how much energy is stored in our energy cell. And it's kind of a tricky condition here because we want to say once the energy reaches 18, we want to turn off the reactor. Once the energy drops below 1, we want to turn it back on, but not turn it off again until it gets up to 18. So we want to sort of run it for as long as we can and fill up that buffer all in one go. So we're going to start with the less than, because we're going to say that if the input energy is less than 1, then we want to output a signal saying run this thing. And because we're going to check that condition or another one, we're going to tie that together with an OR gate. So let's put an OR gate in here. We're going to have 2 inputs, and this is going to be the second one, I think, because we also got to check the upper bound. Now, the upper bound is similar, right? Because we have a less than, and we want to say if the input energy is less than 18, we also want the reactor to run, but only if it's already running, right? Like that's the trick here. We don't want it to always run if it's less than 18. We want it to run only if it's already running. So what we're going to do is create a feedback loop. So we're going to put an AND gate in, and let's see here, make it 2. So the first input to the AND gate is going to be this guy. So basically, if the energy is less than 18 and the system's already running, go ahead and emit a positive signal. So to pull this off, what we're actually going to do is we are going to route the AND or the OR back into the AND. So let's see here, doop, and that guy. So if we are, am I explaining this right? If we are below our current threshold, or let's see, is that right? Let's see, if we are below our current threshold, or the system's already running. Am I setting this up right? Let me think about this for a minute. Yeah. All right. So So we want to say, all right. So if we're less than 1, then the system needs to run, right? If we are less than 18 and the system's running, it needs to keep running. So by pulling this OR back into the AND, if the system's already running and we're less than our threshold, it's going to keep running. And then we're going to actually wind up feeding the AND gate. So in other words, if the system needs to run, into this guy here. So let's go select that, and great. Now that's almost there. We need one more condition on the OR gate. So basically, we want it to be true if the system's already running. And so to do that, what we do is we feed the AND gate back into the OR gate. So let's just walk through the logic here. Let me turn on the wiring so you can see it a little bit better. So we have energy. If energy is less than 1, emit a signal into an OR gate saying that we want the system to run. And we feed that OR gate into an AND gate. So that AND gate says that if the system is told that it needs to be running, then go ahead and we're below our threshold, go ahead and run it. And the trick is that when the system first starts running, it's going to emit back into the OR gate, which is going to be true. So therefore, once the system starts running, it's not going to stop running until this kicks in. I'm pretty sure this is right. So let's go ahead and switch it over to our assembler GUI and back so that we have our schematic. Go ahead and save that. And so this, in theory, should do what we want. So let's go ahead and come over here. We're going to yank this out. Good. Lever came to. All right. We're going to put our casing back in. Now, the great thing about automated redstone is that it reuses components. So you'll actually notice that because there's no schematic, we actually just empty the casing out and we now have our original set of components. So if we switch over, we have our schematic for the energy thermostat. We can now reload this thing. And we don't have enough back planes, I think, is what that's saying. So let me make some back planes real quick. And thankfully, I've got that automated at this point. I'm just going to craft 10. But the thing is that as you improve circuits, you can actually recover pieces you used in the last one. So we now have our new circuit that we're going to bring over here. Okay, so we're going to put our lever back on the front, and now we're going to take this sensor here, and you'll notice there's sort of a sensor and there should be a sensor reader, right? So we're going to put the sensor reader on the side right there, and then we're going to click on that, and we're going to put the sensor in here. Now, here's the thing. The output signal is, a large number right now. And remember, I said we just want small numbers so we don't have to get into 16-bit numbers. So we need a number between 0 and 128. So we're just going to scale this by 4 should do the trick. And actually, we're going to do 5. So now our current output signal is 14 for 14 million. Okay? So now if we configure this again, remember our temperature is on the side, our switch is on the front, and our E is on the left side. And now we can go ahead and turn this on and crank down the rates and turn that on. And we'll note that, there's no fuel. So let's also get more fuel. That would probably be a good idea too. So we're just going to make some more of that uranium. I don't have enough 238. Oh, I've got some more grit. So let's go take this grit and process it. And I really need to set up a rad system because I don't know how many rads I'm getting right now. So I think we had 5 238s, so we probably need 3 more. Okay, that should be enough. Let me come back over here and assemble it, and I'm sure I'm irradiating myself like crazy right now, which is awesome. And the workshop, which is even better. So I'm going to make another 230 LEU 233 because it burns nice and hot for us so that we can actually test the temperature system. Okay, so we are positive. But the energy cell is pretty full right now. So let's see here. Do I have, I think I have an energy. Do I have an energy thing to drain it? I might not. What we want to do is actually drain it. So let me make a thing to, let's see, nullifiers. Yeah, so let's make an energy nullifier real quick. And this just sort of lets us stress test the system because otherwise we'd have to wait for it to drain 14 million RF and it's pulling 230, which is going to take a while. So I'm just going to pop that on top. I'm going to drain out the top. And you can see it's now draining very quickly. And so what we'll do is right before we get to 1 million, we'll go ahead and take the energy drain off the top and verify that everything kicks in as it should. And what should happen is as it runs, it'll sort of run periodically until it's fully charged up to 18 million, and then it should not run for a while. I think if I had been a little more thoughtful, what I would have done is made the range not quite so large so we could actually test it, but too late for that. So we're just going to use our nullifier and burn off a lot of energy. It's not really that expensive in the grand scheme of things. Okay, it's down to 1.2 million. I'm going to let it drain a little bit more. There we go. All right, and you can see it kicked off. Right, it automatically turned on once the threshold was below that. We're now up to 1.1 million, 1.2, but we should see it turn off in a second because it'll be starting to overheat. So let's see if that happens. Yep, it turned off. And now it turned back on because it cooled down. And it turned back on because we said, look, once you're below the threshold, go ahead and activate until you get up to 18. So it's going to keep cycling now until it gets up to 18, which actually won't take it that long in the grand scheme of things. You can just see it turning on or off now. So this is great because now we have a very easy way to basically run the reactor only when we need to. And the rest of the time we run off the energy buffer. So this is kind of perfect, especially if you're on a server with chunk loading and all that stuff. It'll basically, when you're not working somewhere, you'll have a sort of a trickle draw on your energy cell, but your reactor will rarely, if ever, fire. Like with 18 million RF here, my system only pulls 230 per tick. So it's going to be couple hours at least of energy, and if you get into bigger cells, which I do want to get into, it'll run even less often. We can also enable this thing to run hotter. Well, I've got the threshold set pretty low right now. It's responsive enough that we could, in theory, sort of let it get really hot and generate a lot of RF. Now, what this all means is that you can run an unstable sort of reactor because you have a control system in place. And without any penalties for starting and stopping it, it doesn't really matter. I do wonder a little bit if the author of NuclearCraft is going to wind up putting some sort of penalty for start and stop, because in theory you shouldn't build a reactor like this. It takes time to get going and warm up and stuff. But anyway, so that is the whole thing. That is our control circuit. And sorry you had to bear with me through this fumbling. This is actually, this kind of and/or configuration is actually called a flip-flop, and I think it's an SR, a state or a set and reset flip-flop. You can do slightly more efficient setups, I think, but this is what I came up with and managed to make work. So it's pretty powerful idea and lets you sort of have fine-grained control. I guess that's about it for today. So we now have a reactor that we can run in a very in an unstable way. It's going to only run when it absolutely has to, and run off. The rest of our system runs off batteries whenever it can. And if you complement that with a renewable system, even a small one, it's very likely that under normal circumstances you're just never gonna. Your reactor is going to turn on very rarely, and when it does turn on, it'll run for a while. So anyway, that's what we have. I hope this was useful. It was a lot of fun doing this build, and we'll see what we come up with next time. But that's this part of NuclearCraft. Thanks. Bye. Hey, I just realized that there's a bug in the last video, or at the beginning of this video, and before signing off, I wanted to make sure I fixed it for you. So what was happening is that the input sensor, so when the cell was full, the input sensor was still outputting 17, even though it was totally full, and it was actually registered as 18 million. I think it's just a rounding error. So what I did was I came over to the designer and I changed this constant from 18 to 17. So basically saying as long as the energy, the upper threshold is, as long as there's less than 17 million in the buffer, that's when we want to run. So it's really important to get these sort of off by one errors fixed, and I just wanted to call that out. So simple little fix, but definitely worth doing. Otherwise, what's going to happen is this thing will never shut off and you'll waste a lot of energy. So I learned that the hard way, and I thought I'd share it with you. And that's about it. Thanks. Bye.